All right, so in keeping pace, let's continue on. And the statement reads, in writing equations 9.76 and 77, I tactically assumed that the reflected and transmitted waves have the same polarization as the incident wave along the x direction. Prove that this must be so. That's fair to say, I would think. Hint, let the polarization vectors of the transmitted and reflected waves be for the polarization direction for the transmitted is equal to cosine theta t, x sine theta t y, pretty standard, and same thing for the reflected, and prove from the boundary conditions that theta t and theta r equals 0. Okay, so we're going to get the same direction for the x polarization direction. All right, so what we need to know, clearly our boundary conditions. The parallel for the E has to have that E naught I plus E naught R equal E naught T. Again, all tildes. Same thing, parallel for B, except we have to have the reflection is negative on it because it has to be perpendicular to the opposite direction of E. That's the only big thing here. And then again, transmitted beta has to be there since we're in the new medium for B. Yeah, so beta is equal to mu1 V1, mu2 V2. All right, so for our solution, if we look at the boundary condition for the parallel components of E and B, we can replace it with the directions here. So we have E naught I x hat plus the E naught R propagation direction in R, and we have E naught T propagation direction in T. And if we plug those in from what was given, and we see this is plug it in, move it around, see how it is. And further, we see that E naught I z cross x hat minus E naught R z cross n hat R equal beta E naught T z hat cross n T. Again, we got that from how to get the field of the, how to get the magnetic field from the electric field propagation direction time or cross the product with the polarization direction. So that's why we see the cross products there for the E and B field boundary conditions. All right, so once we're there, we see that the magnetic field goes to magnetic field boundary conditions simplified E naught I y hat minus E naught R with everything after the cross product. So z cross x gives us y, and then z cross y gives us negative x. Similarly, on the transmitted side, we get z cross x gives us y, and z cross y gives us negative x. So yeah, go ahead and put that there. So if we isolate this to the y component of the E equation and the x component of the B equation, we see that. Okay, so all we're trying to do is match component-wise. So x and y, so we want to isolate to the y component, so we get the reflections there all together. We see that we have tilde E naught R sine theta R is equal to the epsilon E naught T sine theta t. So what we're trying to do is translate this down. Let's keep pushing it forward. Okay, that was from the electric component, and and from the magnetic component, we see what happens there. And so you see these two equations are similar but different by a factor of beta and a minus sign. So substituting this into one another for E naught R sine theta R and pushing it together to find what theta t is, what we see is that the complex coefficients for the transmitted cancel, and we're left with sine theta t is equal to negative beta sine theta t, which tells us that beta is equal to negative 1. This can't be true. Or if that's the case, then sine theta t has to equal to 0, which only happens at theta equal t or theta t equals 0. It could happen in other spots, but we're looking at the primary or principal root. So back substituting this, we get E naught r sine theta r is equal to 0 from the first equation. And again, this shows us that theta r equals 0, thus theta t plus equals theta r equals 0. So, pretty cool thing to say, but again, this is just form matching. I wouldn't say anything too crazy, but good idea to verify that the reflection polarization is the same polarization of the incident.